Ah, the science fair. That time of year that rolls around when students start thinking about creative ways to relate science to the real world, and they come up with a lot of unique ideas, like a whole bunch of volcanoes. Baking soda and vinegar are what power these volcanoes. Vinegar is acetic acid. It has the chemical formula HC2H3O2. This is the way we write the formula in an inorganic chemistry class, and that's how you usually see it in an introductory class in high school. Sodium bicarbonate is the baking soda, and it has a chemical formula of NaHCO3 with the bicarbonate polyatomic ion. We talked about the chemical formulas of acids and bases in the last video, and we talked about Arrhenius acids and bases and how an Arrhenius acid was defined as a substance that would produce hydrogen ions in solution. And so all of the Arrhenius acids began with the element hydrogen or hydrogen ion, which is what we see with acetic acid. We also talked about Arrhenius bases. These substances are defined by their ability to produce hydroxide ions in solution. But if we look at sodium bicarbonate, it does not have the hydroxide ion. And yet, as you probably have remember from elementary school, when you probably saw the same type of experiment in your science class, sodium bicarbonate is in fact a base. It's just not an Arrhenius base, which brings us to the topic of different theories of acids and bases. Let's start with the Arrhenius acid-base theory. This is the one that we looked at in the last video. An Arrhenius acid is a hydrogen ion producer, and because it produces hydrogen ions, it increases the hydrogen ion concentration in a solution. For example, if we have pure water, that means that we have a whole bunch of H2O floating around, and a very, very small amount of that substance actually does break apart into H plus and OH minus ions, but we'll talk more about that later. When you add hydrochloric acid into this pure water, you make a solution of HCl, and you'll notice if you look at the image on the right-hand side that you have chloride ions and hydrogen ions that have been added to the solution. Well, the chloride doesn't do much, but the hydrogen ions do make this an acidic solution. It's what gives it those properties of an acid that we talked about in the last video. And you'll see that you have the hydrogen ions coming from the hydrogen chloride or the hydrochloric acid. And you've got chloride ions floating around in there as well, but the hydrogen is really what is giving it the acidic properties. An Arrhenius base is an hydroxide ion producer. Hydroxide is the polyatomic OH minus. And an Arrhenius base is going to be a substance that increases hydroxide ion concentration in solution. So again, we have our sample of pure water, and if we add NaOH to it, we end up with a whole bunch of extra OHs. Yes, the water does have some of them, and there's some H pluses from the water as well, but you have a whole lot more OH ions than you have hydrogen ions, a lot more hydroxides present in a solution. And that is what gives this substance the properties of a base that we talked about in the last video. So looking at water, again, in a pure sample of water, you have some amount of hydrogen and hydroxide ions. There's a constant that defines this amount that we'll go into later, but you have this because of the self-ionization of water. Basically, two water molecules will collide with each other with the right amount of energy, and you'll form one of them will donate a hydrogen to the other, and you'll form hydronium and hydroxide. Or simplified, we write this as a hydrogen ion and hydroxide, as you see in the image on the right hand side. Because water makes hydrogen ions in solution, It's considered to act as an acid by the Arrhenius definition, but it also makes hydroxide ions, which means it also acts like a base. In actuality, water is chemically neutral, but in certain circumstances, depending on what it is that it's mixed with, it can act as an acid or as a base, and we'll talk about that with one of the next theories. The Arrhenius definition of the acid and base has limitations. It's not a very good definition, but it's the first one that we had. First problem with it is that it's restricted to aqueous solutions. So when we talk about acids and bases, according to the Arrhenius theory, we're talking about solutions, things that are dissolved in water. Many substances that we know to be bases don't produce hydroxide ions, like the baking soda that we looked at a minute ago, which would not qualify them as bases according to the Arrhenius definition, and yet we know that they are in fact bases. Things like Windex, which contains ammonia, or Tums, which contains calcium carbonate, or baking soda, again, sodium hydrogen carbonate or sodium bicarbonate. These don't fit that definition, but they do fit another definition, a more broad one, and that definition is the Bronsted-Lowry Theory of acids and bases. It doesn't sound that different whenever you look at the definition of an acid. Bronsted and Lowry were two scientists who came up with the same basic definition for acids and bases. And the acid definition is really pretty similar to the way that Arrhenius had defined it. An acid is a hydrogen ion or proton donor. The definition of the base is what sounds a little bit different. The base is defined as a hydrogen ion or proton acceptor. So instead of defining one of them as producing hydrogen ions and the other as producing hydroxide ions, the Bronsted-Lowry definition makes them opposites. One other thing I want to touch on is why it says proton. What is a hydrogen ion? Well, if you look at a hydrogen atom, it is an atom that has one proton, typically 0 neutrons, and 1 electron. When we talk about hydrogen ions, they're the cations that we see in our acids, those H+ ions. What that means is that it has lost an electron. So hydrogen ion is simply 1 proton with 0 electrons and 0 neutrons, which means that it is just, in actuality, a single proton, which is why hydrogen ion or proton donor is the definition. They're actually the same thing. But this adds to the Arrhenius theory. Substances that produce hydroxide ions, which was the Arrhenius definition of a base, those substances are still considered to be bases because they accept hydrogen ions to form water. But now our definition is more broad and more accurate. So this isn't actually taking away or contradicting anything. Those same substances that we considered bases a minute ago are still bases now. Again, Bronsted and Lowry defined it as a hydrogen ion or proton acceptor. So let's look at a sample of NaOH in solution. You can see the pink sodium ions and the red and white hydroxide polyatomics there, and I've got water molecules that are in blue. But what we see happening whenever these two substances are mixed together is we see hydrogen being attracted to that hydroxide. Okay, so the hydroxide, which had a negative charge, will attract one of the hydrogens from the water, making the hydroxide a hydrogen ion acceptor and thus a base. So again, something like sodium hydroxide is in fact a hydroxide ion producer, but it's also a hydrogen ion acceptor. And so it fits both the Arrhenius definition and the Bronsted-Lowry definition. You can see here, again, just looking at one of them in isolation, hydroxide, when added to water, the sodium's not doing anything, so I'm leaving it out. You'll see a transfer of a hydrogen from the water molecule to the hydroxide and forming water where we used to have hydroxide and hydroxide where we used to have water. All right, so what exactly is happening in a Bronsted-Lowry acid-base reaction? Well, To put it simply, a base takes a hydrogen ion from an acid. That's what's happening. The base is taking the hydrogen ion from the acid. So if we look at this example below, we have water and HCl, and we're producing H3O and Cl minus, 2 ions. The question says, which chemical species is behaving as an acid in the diagram below, and why? Well, again, if we look at our simplified definition, a base takes a hydrogen ion from an acid. So the acid is the one that is donating the hydrogen ion. And if we look at our before and after in this chemical equation that we see at the bottom, the one that has donated its hydrogen ion, or had it stolen, depending on how you look at it, is the HCl. HCl went from having a hydrogen ion attached to it to not having one and just forming a chloride ion. So our acid, according to the Bronsted-Lowry definition, is the HCl. The base, according to the Bronsted-Lowry definition, the one that takes the hydrogen ion, is therefore the water, because it goes from being H2O to being H3O plus. All right, so we can kind of see a connection between the products and the reactants here. You notice that they differ by 1 hydrogen ion. And we call, obviously we've classified our reactants here as either Bronsted-Lowry acids or Bronsted-Lowry bases, but we can also classify the products that are formed as either conjugate acids or conjugate bases that differ from the Bronsted-Lowry acid and base by 1 hydrogen ion. So if we look at this equation, we have ammonia, NH3, plus HCl, producing ammonium ion, NH4+, plus the chloride ion. And again, if we think back to our definition, a base takes a hydrogen ion from an acid. So if we look at what's happening here, who's taking the hydrogen? Well, that's pretty clear. It's the NH3. The NH3 is taking the hydrogen to become NH4+. Because it takes the hydrogen, we call it the Bronsted-Lowry base. The HCl, on the other hand, is donating the hydrogen, and so it is classified as the Bronsted-Lowry acid. But we see a relationship between the left and the right-hand side of this equation. The substance NH4 is formed because it has gained a hydrogen ion. But we could look at this reaction in reverse. That's why there's a double-headed arrow in the middle. We could say that now that we have NH4 plus and Cl minus, we could see it going back to what we started with, where now the NH4 plus could have its hydrogen taken away by a chloride. It's therefore called a conjugate acid. NH3 was our base. NH4 plus is therefore our conjugate acid. Cl minus is therefore our conjugate base. If you identify what the Bronsted-Lowry acid and base are in your reactants, then the conjugate acid and the conjugate base are pretty easy to identify, because whatever substance you classified as the Bronsted-Lowry base, in this case NH3, is going to form your conjugate acid. So NH3 forms a conjugate acid, NH4+. They differ by 1 hydrogen ion. Whatever substance you classified as your acid, in this case HCl, is going to form the conjugate base once it has lost its hydrogen ion, because at this point the conjugate base, Cl minus, could take a hydrogen ion from the conjugate acid in the reverse reaction. Chemical reactions can sometimes be read from, or usually we read them from left to right, but can sometimes be read from right to left in a reverse reaction. And that's the case here. All right, so let's see if we can identify what substances we have in these equations. H2O plus H2SO4 yields H3O plus HSO4 minus. And my charges are left off here, I'm not sure why, but H3O should be H3O plus and HSO4 should be HSO4 minus. Well, if we look at this, again, the base takes the hydrogen ion from the acid. look at the right-hand side. Which one has taken the hydrogen ion? Okay, which one took it? Was it the water on the left or was it the H2SO4? Well, clearly it has to be the water because it turns into H3O plus. It had to have taken one of those hydrogens away, which means that water is our base in this equation. H2SO4 is therefore our acid. Because it forms H3O plus, because water forms H3O plus in this reaction, and water is the base, H3O plus is therefore the conjugate acid. And because our acid, H2SO4, having lost a hydrogen, becomes HSO4 minus, it produces what is known as our conjugate base. All right, NO2 plus H2O yields HNO2 plus OH minus. And here again we have OH minus, and we should have an NO2 minus on the left-hand side. I don't know why the charges were left off. But if we look at this, which one is taking the hydrogen? Well, going from left to right, we can see that NO2 has taken a hydrogen because it becomes HNO2, which means that it is our base. It's the one that takes the hydrogen. The acid is the one that donates the hydrogen, and H2O, having lost a hydrogen, becomes just OH minus, or the hydroxide ion. So our base is NO2 minus, our acid is H2O, and then our conjugate acid, which forms from the base, is HNO2, and our conjugate base, which forms from our acid, is OH minus. The third one, we have water as our acid, cyanide as our base, that should be Cn minus. Our conjugate base is hydroxide, our conjugate acid is hydrocyanic acid. Again, just look at which one is donating hydrogen, which one is accepting it. And again, our last one, HCl plus HCO3 minus, is going to yield H2CO3 and the chloride ion Cl minus. All right, so that was the Bronsted and Lowry definition. The last definition is the most broad of all, and it is the Lewis acid-base definition. Lewis defined acids as electron pair acceptors and bases as electron pair donors. Again, this isn't going to conflict with anything, but rather add to it. It's going to extend the definition because now we don't even have to have hydrogen in order to classify something as an acid. We don't even have to look at hydrogen in order to know if we have an acid or a base. So again, if we look at the Lewis definition, we're just looking at it from a different point of view. The transfer of electrons versus the transfer of protons. If we look at our example, NH3 plus HCl, NH3 we already classified as a base, which means it's an electron pair donor. Well, look at it. It has a pair of electrons in my little cartoon drawing here on our gentleman's arm, and he is going to donate them in order to form a bond with the hydrogen. And he's going to take the hydrogen from the HCl in order to bond with it. The acid, HCl, is the electron pair acceptor. It is accepting the pair of electrons that has been donated by the base. Okay, so again, NH3 was a Bronsted-Lowry base because it accepts a proton. NH3 is also a Lewis base because it donates a pair of electrons. In fact, any atom containing a lone pair of electrons could be classified as a Lewis base. If you've got a lone pair sitting on anything, it could be a Lewis base under the right circumstances if you have something that can accept that pair. Okay, so anyway, this is just a different point of view. Again, does not conflict with anything, does not change the way we classify. It just makes it broader. It includes more substances that don't necessarily have hydrogen in them, because you could have something where you have no hydrogen involved at all. All right, so summary of our acid-base theories. The Arrhenius definition defines an acid as a substance that produces hydrogen ions in solution, and a base as a substance that produces hydroxide ions in solution. It's the most restrictive definition because it requires that the base have hydroxide in it. Bronsted and Lowry came up with a little bit more broad of a definition, where an acid is defined as a proton or hydrogen ion donor, really not that different from the Arrhenius definition. But the base was defined as the opposite of that, the opposite of the acid. In this case, a proton or hydrogen ion acceptor, which opens us up to more possibilities because now our base doesn't have to have hydroxide in it. The Lewis definition is the most broad of all because now we don't even have to have hydrogen. A Lewis acid is defined as an electron pair acceptor, whereas a Lewis base is defined as an electron pair donor. And it really does help with these types of acids and bases to actually draw out the Lewis structures to see where the bond is occurring.